Well, there certainly can't be a title more impressive than this one, The Fundamental Theorem of Algebra. This is what we're about to talk about, the fundamental theorem. First, we need a little bit of vocabulary. A linear factor is a factor of the form ax plus b. I think I've used these words before, actually, in the course. And just in parentheses, I say, of course, a could be the number 1, or a different number. B could be negative, so we could have a minus sign. So some examples of linear factors are just those factors we're used to writing in parentheses. X plus 3, x minus 5, 2x plus 3, 3x minus 7. X plus the square root of 2 is a linear factor, so you could have square roots or other kinds of numbers. They don't have to be integers. I note here too that even x by itself can be a linear factor. We can think of this as this x as 1x minus 0. And I want to just give us an example of that. Like if you have a polynomial that factors as x times x minus 2 times x plus 3, this is the way we would normally write the factorization, but in your head sometimes it's helpful to think of that x is like a x minus 0. So just like these other factors correspond to x-intercepts, like plus 2 is the x-intercept for x minus 2, minus 3 is the x-intercept for x plus 3, 0 is the x-intercept that corresponds when we see a factor of x all by itself. Another example I have here on the handout is x cubed minus x squared plus 4x minus 4. We just worked that example, right? And we factored it. When we factored it completely, we got x minus 1, x minus 2i, x plus 2i. So just notice that if we allow complex numbers, every polynomial of degree 3 has 3 linear factors, and thus 3 complex zeros counting multiplicities. We'll talk about multiplicity again in a second. This is really the gist of what is called the fundamental theorem of algebra. And here it is in a red box. Every polynomial of degree greater than or equal to 1 has a 0, possibly a non-real complex number. Now this is the traditional statement of the fundamental theorem, and to me it's kind of a letdown kind of statement. It's not that exciting. So I just wrote beneath it, this implies that, and what I underlined here I think is maybe a better or more useful way to think of what the fundamental theorem is telling us, because the fundamental theorem implies that every polynomial of degree n factors into n linear factors as long as we allow complex numbers as zeros. If we don't have complex numbers, we'll get stuck in the factoring. Like in that example up above, we wouldn't be able to get beyond x squared plus 4, which is not a linear factor, without complex numbers. But complex numbers allow us to get to a list of all linear factors. So what I underlined here in red is really the way I think of the fundamental theorem. And if we have n linear factors, then every polynomial of degree n has n zeros counting multiplicities. And we'll look at an example of this in a second. So just before we go on, I made a yellow card because I think this is an important theorem. And yet what I've highlighted here is not what I put in the box, but what I underlined in red below it, that every polynomial of degree n factors into n linear factors if we allow complex numbers. That's really the powerful result of the fundamental theorem of algebra. So let's look at an example. And let me position things here. So This is not an example that we looked at before. I went ahead and worked through this ahead of time on my own. So it's a polynomial of degree 4. X to the 4th plus x cubed minus 3x squared minus 5x minus 2. And I went ahead and found the zeros and factored it on my own ahead of time. So you can check this by multiplying this out. You don't have to, but you can if you want to verify. It factors into x plus 1, x plus 1, x plus 1, x minus 2. So that line is what we call 4 linear factors. So the fundamental theorem says if you're of degree 4, you're going to get 4 linear factors. Now, notice that we also say there are 4 zeros counting multiplicities. That counting multiplicities is the fine print, because you'd say, well, there are only 2 zeros. -1 is a 0 and +2 is a 0. But see, -1 is a 0 of multiplicity 3 because it occurs to the 3rd power. 2 is a 0 of multiplicity 1. So you might not like the way we say this, but we say there are 4 zeros counting multiplicities because we kind of count -1 3 times because it has 3 factors of x plus 1. And we count 2 just once. So this is an illustration of the fundamental theorem at work with actually the factors and zeros are all nice numbers, no ugly looking square roots or complex numbers involved there. Now we need one more vocabulary term because we actually have one more theorem coming up. And the vocabulary term that we need is complex conjugates. If a plus bi is a complex number, so where a and b are real numbers, then a minus bi is called the complex conjugate of a plus bi. Now let's think about what this is saying here. Here are some examples. 1 plus 2i and 1 minus 2i are complex conjugates. We also say 3i and minus 3i are complex conjugates. We also say the complex conjugate of any real number is the number itself. Now you might say, wait a minute, this is getting a little weird. The first line made sense, but what's the rest of this? So I made a little chart here just to help clarify this. The complex number 1 plus 2i has a plus bi form 1 plus 2i. So change the plus sign to a minus, you get the conjugate, 1 minus 2i. The complex number 3i, all by itself, has a plus bi form 0 plus 3i, is the way we think of that. So its complex conjugate is 0 minus 3i, which simplifies to just minus 3i. Now normally we don't write the 0 down at all, we just say 3i and minus 3i are complex conjugates. So that kind of explains that one example up above. Now what if you took a real number like 5, just a real number, its a plus bi form is 5 plus 0i, and so its complex conjugate would be 5 minus 0i, and do you see that's still just 5? That's what we mean by saying a real number is its own complex conjugate. Now here's our last theorem that you just got to know, and it's an important one, the complex conjugate theorem. If a complex number with non-zero imaginary part is a 0 of a polynomial with real number coefficients, then its complex conjugate must also be a 0. So I summed this up on a yellow card too, and I sort of wrote it in my own words, complex conjugate theorem. Let p of x be a polynomial with real coefficients. If a plus bi is a 0 of p of x, then a minus bi is also a 0. We call these complex conjugate pairs, and they always come together as pairs of zeros of a polynomial. You never have one without the other. So let's just, I think I want to look at one example before we do a problem. I think well, yeah, let's just look at this example, and then we're going to cut off the video and we'll do the exercise in the next. In an earlier problem, we saw that both 2i and minus 2i are zeros of this polynomial. That was an example that we worked out together. So in the next portion, we'll do example 5, where we're going to look at another pair of complex conjugate zeros.